So I welcome you all to the YouTube platform of IMS GATE Academy. Myself Prateek Mishra. Just confirm me once whether my voice is audible or not. Voice is audible to you? Just confirm me once whether my voice is audible or not. Just confirm me once whether my voice is audible or not. Okay. Just check once. Okay, so it's audible. Okay. So again, I welcome you all to the YouTube platform of IMS GATE Academy. Myself Prateek Mishra, and we are running this foundation courses, and we also run the courses on most expected concept for GATE-24 for environmental engineering. My dear students, along the long way, we have already seen many concepts that are important from GATE point of view. Okay, thank you Thiru sir, thank you so much. Yeah, thank you so much. Okay, so we have seen so many concepts that are important from GATE point of view. Today we will going to see one of the very important concept for environmental engineering, that is activated sludge process. My dear students, the entire environmental engineering has different sections: raw water engineering, wastewater engineering, then you have air pollution, and then you have solid waste management. When I talk about the wastewater engineering, for wastewater engineering, the topic which is of high importance is the biological treatment. In the previous session, we have seen how many types of biological treatment we can give. It can be a trickling filter, it can be rotatory biological contractor, it can be activated sludge process, it can be upflow anaerobic sludge blanket reactor, it can be a septic tank, it can be an IMOF tank, it can be an oxidation pond. So out of all these biological treatment processes, we give one in our treatment of wastewater. So today we will going to see one such treatment which is termed as activated sludge process. So today's topic of discussion is activated sludge process. Activated sludge process. Now whenever question happens from this topic, there are so many confusions to the student, what to calculate, how to calculate, all those. And this is one of the most critical area when you talk about the entire environmental engineering. So we will going to deal with all those basics and the definitions from where the questions are asked from the activated sludge process. My sincere request to you is just watch this video till the end so that all your doubts regarding this segment of environmental engineering will be cleared. In the examination, there are high chances that the question can be framed from activated sludge process. By the end of the lecture, you will get the reason why there are so much chances of getting a question from activated sludge process. So I'll start with this. First of all, this activated sludge process is a biological treatment given to wastewater. And when I talk about any type of biological treatment, it is done for the removal of dissolved organic solids from the wastewater. So this activated sludge process is also performed to remove dissolved organic solids It is also done to remove dissolved organic solids which is present in the wastewater. If I talk about wastewater, especially this wastewater which is generated after domestic activity, the major impurity is the organic matter. Suspended organic matter we have already removed in the primary sedimentation tank. Now we perform the biological treatment for the removal of dissolved organic solids from the wastewater. This activated sludge process has two parts or two segments. So we have the wastewater from the primary sedimentation tank, which is PST. We have this settled water from the primary sedimentation tank, PST. This water is sent to the aeration tank. This water is sent to the aeration tank. Okay, so aeration tank I'll write here. Okay. inside the aeration tank, decomposition of the organic matter will happen. How it is happening, that is a point of discussion. But for now, we are sending wastewater from PST to aeration tank. That is the first segment of activated sludge process. After decomposition inside the aeration tank, whatever biomass is produced, that biomass is settled in the secondary sedimentation tank. So from the aeration tank, the wastewater is taken to the secondary sedimentation tank where this biomass is settled. So this is my secondary sedimentation tank, where whatever biomass is produced inside the aeration tank, it is settled in the secondary sedimentation tank. So at the bottom of the secondary sedimentation tank, this is the sludge which is produced, and this sludge is of biomass. This sludge is of biomass, and biomass is decomposed organic matter. Again, I'll repeat this. Wastewater is sent into the aeration tank where microorganisms carry out the decomposition of the organic matter to form the biomass. Then the biomass produced is settled in the secondary sedimentation tank. So whatever sludge we will get from the secondary sedimentation tank, this sludge is of the biomass, and this biomass contains active microorganisms. This biomass contains active microorganisms. This biomass contains active microorganism. So the sludge produced inside the secondary sedimentation tank, this sludge is of biomass containing active microorganism. Then this sludge is recirculated back into the aeration tank just to increase the number of microorganisms inside the aeration tank. This sludge is recirculated back into the aeration tank, right? So this is known as recirculated discharge. Now, why this sludge is recirculated back into the aeration tank? In order to increase the number of microorganisms inside the aeration tank. And if we increase the number of microorganisms inside the aeration tank, it means that now more microorganisms will be carrying out the decomposition of the organic matter. Since we are recirculating this sludge which contains active microorganism, therefore this sludge is known as the activated sludge. This sludge is known as the activated sludge. This sludge is known as the activated sludge. And since we are recirculating some amount of activated sludge inside the aeration tank, therefore this process is named as activated sludge process. I think this is very simple to you. Wastewater from the primary sedimentation tank, where all the suspended organic matter is removed. This wastewater is taken into the aeration tank where it is brought in contact with the microorganism. Inside the aeration tank, microorganism will carry out the decomposition of the organic matter to form biomass. This biomass from the aeration tank is taken to the secondary sedimentation tank along with the wastewater, and this biomass settles inside the secondary sedimentation tank. So this biomass, which contains active microorganism, is recirculated back into the aeration tank in order to increase the number of microorganisms inside the aeration tank. Since this sludge contains active microorganism, hence it is referred as activated sludge. And this entire process is termed as activated sludge process. So this is the outline of activated sludge process. What is actually happening? If you understand this basic of activated sludge process, then we can go for further analysis, right? Most of the student has difficulty in understanding this mechanism. What actually happens inside the activated sludge process? So this entire system of recirculating back the activated sludge into the aeration tank, this entire system comprises the activated sludge process. Okay, let's start one by one. First of all, We'll start with this. So you have microorganisms. These microorganisms, in the presence of oxygen, will carry out the decomposition of organic matter. Microorganisms, in the presence of oxygen, will carry out the decomposition of organic matter to form biomass. And this biomass is nothing but decomposed organic matter, and over this biomass, these microorganisms will stay. So again, I'll repeat myself. In order to represent the amount of organic matter present in the wastewater, we represent it through the organic matter. We represent it through the BOD of the wastewater. So in order to represent the organic matter present in the wastewater, we represent it through the BOD. In order to represent the microorganism present in the wastewater, we represent it through MLSS concentration. MLSS concentration or MLVSS concentration. That is nothing but the amount of biomass present in the system. More the biomass, more the active microorganism, more will be the decomposition of the organic matter, right? So while discussing about biochemical oxygen demand, we have seen this curve. If this is my organic matter in the system, let me draw this curve again. If this is my organic matter at time t is equals to 0, denoted by L0. This organic matter under the attack of microorganism will keep on decomposing, and this decomposes like this. This is how organic matter decomposes inside the system, okay? At the same time, at L0, at time t is equals to 0, if you add microorganism in the system, now we need to analyze how these microorganisms will grow. At time t is equals to 0, if you are adding some microorganism, their growth follows like this. Their growth follows this curve. This is the growth of microorganism in the system. This is the growth curve for microorganism, okay? Now when you look into the initial part, you have to analyze both. When you look into the initial part, so this is the growth curve for microorganism that I have drawn in yellow. So in yellow, it is representing microorganisms in the system, okay? Initially, when you add microorganism to the system, these microorganisms will not immediately carry out the decomposition, and even they immediately not grow in their colonies. Initially, when you are adding microorganism to the system, they will take some time to get friendly with the surroundings. And you see the minimum growth of microorganism in this phase. So this first phase where the minimum growth of microorganism is observed because microorganisms are getting friendly with the surroundings, this phase is known as the lag phase. So this is my phase number 1. This phase is known as the lag phase. So first phase for the growth of microorganism, so I am writing here, growth of microorganisms follows 4 phases. First phase, phase 1, is known as the lag phase. First phase is known as the lag phase. In lag phase, the microorganisms are getting friendly with the surrounding. Here in the curve you can clearly see, in this first phase, sufficient availability of food is there, enough food is available, but microorganisms are first getting friendly with the surrounding. That's why they are not actively carrying out the decomposition, and they are not even multiplying in numbers also, right? That's why the growth in this phase is less. Now comes the second phase. This is the second phase of the growth of microorganism. In the second phase, the microorganism has become friendly with the surrounding, and even sufficient availability of food is there. You can see two curves, one drawn with yellow, another one with white. So this yellow curve tells us that there is a huge increase in the colonies of microorganism. And why this happened? Because in this phase, microorganisms are already friendly with the food given to them. That's why they start actively decomposing this organic matter and even multiplying actively in numbers. So this phase where you see the abrupt growth in the microorganisms is termed as the log phase. This is the log phase. Phase 2 for microorganism growth is termed as the log phase. Phase 2 is log phase. In phase 1, microorganisms are getting friendly with the surrounding. In phase 2, now the microorganisms are already friendly with the surrounding. They actively start decomposing the organic matter and they start multiplying in numbers. Now comes the third phase. When you look into the third phase, in this third phase, deficiency of food starts after some time. Right? You can clearly see the peak in this phase. From this point to this point, there is no problem. But beyond this point, the deficiency of food starts happening inside the system. And whenever deficiency of food starts happening inside the system, microorganism starts undergoing endogenous respiration. That is, they start killing themselves. That's why you see the decrease in the number of microorganisms. So in this phase, since the growth of microorganism is stationary, you can clearly see these two lines, right? The growth of microorganism is stationary. At the starting of this phase, this is the number of microorganism. At the end of this phase, this is the number of microorganism. Since the growth of microorganism is stationary, therefore this phase is classified as the stationary phase. So third phase in the growth of microorganism is classified as stationary phase. This is stationary phase. Now when you look into the next phase, in the next phase, there is huge deficiency of organic matter or there is huge deficiency of food, due to which there is abrupt decrease in the number of microorganisms. Since due to deficiency of food in this phase, more and more microorganisms starts undergoing endogenous respiration, that they start killing themselves. That's why you see the negative growth of microorganism, means more and more microorganisms will get killed and leave the system. So this phase is known as the endogenous phase. So this phase is known as the endogenous phase. So this is phase 1, phase 2 and phase 3, phase 4. So phase 4 in the growth of microorganism is known as endogenous phase. This is known as the endogenous phase. So these are the 4 phases in the growth of microorganism. So whenever we are analyzing how the microorganism will grow, we have to see 2 things. First of all, microorganisms are in which phase. Second is how much food is available to them. Initially, microorganisms get friendly. That's why you see minimum growth, and that is known as the lag phase. When the microorganisms become friendly to the organic matter, you see abrupt growth in the number of microorganisms, that is known as the log phase. Third phase is when, after some point of time, deficiency of food starts and deficiency of food happens and some microorganisms starts undergoing endogenous respiration, that they start killing themselves. That is known as the stationary phase, as the growth of microorganism is stationary. After this phase, Due to heavy deficiency of food, more and more microorganisms will kill themselves by undergoing endogenous respiration. So this is known as the endogenous phase. 4 phases for the growth of microorganisms. Okay. Now this organic matter is represented in terms of BOD. This organic matter is represented in terms of BOD, and microorganisms are represented in terms of biomass, X. BOD for organic matter, for microorganisms, biomass. So let's see the kinetics for this. So first one is food. How the kinetics of food will go is, so decay of food is represented by BOD. And how the BOD is decreasing? So the decay of food minus ds by dt. Since food is decreasing, so that's why minus sign is there. Minus ds by dt is directly proportional to the BOD present after any time t, that is S. S is nothing but the BOD after any time t. So when you remove the proportionality sign, you have minus ds by dt is equal to Kd into S. You say St. So this is the decay of food in the system, where Kd is termed as deoxygenation rate constant. This is known as deoxygenation rate constant. Okay. So this analysis we have already seen while we were discussing for BOD. Okay. Over the period of time, the organic matter will decay, and this is how it decays. The rate of decay of food is directly proportional to the food present in the system. So minus ds by dt is directly proportional to St, and St is nothing but the food present in the system after time t. So minus ds by dt is equal to Kd into St. So this is our first expression related to food. Now second one is for microorganisms. Second one is for microorganisms represented by biomass. So first one is growth of biomass. So growth of biomass dx by dt is directly proportional to the amount of biomass present in the system. Dx by dt is directly proportional to the amount of biomass present in the system. So when you remove the proportionality sign, you have dx by dt is equal to k into x. Here k is known as overall growth rate constant, where k is known as overall growth rate constant. Where k is known as overall growth rate constant. So this is the growth of biomass in the system. And up till which point this growth will happen? This growth will happen in the lag phase, in the log phase, and at some part of the stationary phase. When the deficiency of food will start, then decay of biomass also starts happening. So next is how the decay of biomass happens. Second one is decay of biomass. So again, the decay of biomass minus dx by dt, this is the decay of biomass, is again directly proportional to the amount of biomass present in the system. Removing the proportionality sign, you have minus dx by dt is equal to KER into x. So you write this dx by dt minus KER into X. This is the decay of biomass, where KER is known as endogenous decay rate constant. KER is known as endogenous decay rate constant, right? Now, when you have to see the overall change in the biomass, you have to take up growth of biomass and decay of biomass simultaneously. So, the growth of biomass is dx by dt is equals to k into x, and the decay of biomass is dx by dt is equals to minus KER into x. So, overall change in biomass can be written as like this. So, overall change in biomass can be written as dx by dt is equal to K minus KER into X. This is the overall change in biomass. Dx by dt is equal to K minus KER into X. This is the overall change in biomass. Okay. Now this you have to keep a check what you are analyzing. Whether you are analyzing decay of biomass, so this expression has to be used. If you are analyzing growth of biomass, then this expression has to be used. Okay. And when you want to see the overall change in the biomass, then for that you need to go for this expression. This is the overall change in biomass, where we are adding the growth of biomass and also the decay of biomass. Okay. So this is the first expression related to your activated sludge process. Now starting with this, so basically wastewater from primary sedimentation tank, PST, wastewater from primary sedimentation tank is taken to the aeration tank. Where sufficient availability of oxygen is maintained. So here I'll draw oxygen. Sufficient availability of oxygen is maintained inside the aeration tank. Okay. Wastewater from primary sedimentation tank is taken to the aeration tank. The wastewater which is coming from the primary sedimentation tank has discharge of Q0, has BOD of S0, has biomass concentration of X0. What is Q0? Q0 is the discharge of wastewater. S0 is the BOD of wastewater entering into the aeration tank, and X0 is the MLSS concentration or the biomass entering into the aeration tank. This X0 is nothing but the number of microorganisms which are coming along with the wastewater. Now inside the aeration tank, what we will do is, in order to initiate the process, we will going to add microorganisms from our side. What I said, in order to initiate the process, we will going to add microorganisms from our side inside this aeration tank. And these microorganisms will be present in suspension like this. These microorganisms will be present in suspension like this. Okay. In order to initiate the process, just for initiating the process, we will going to add microorganisms from our side. And these microorganisms will be present in suspension like this inside the aeration tank. Now, these microorganisms which are present in suspension will carry out the decomposition of the organic matter, And from our side, we have ensured that sufficient availability of oxygen is maintained. That's why activated sludge process is first of all the aerobic system, because here the decomposition is happening in the presence of oxygen. Second, microorganisms are present in suspension inside the aeration tank. We haven't provided any medium for the attachment of the microorganism or the biomass layer. That's why this system is classified as suspended growth system. So activated sludge process is an example of aerobic suspended growth system. Again, a very favorite statement can be framed for your multiple select question. So what is your activated sludge process? So I'll write here. Activated sludge process is your this is your aerobic suspended growth system. So activated sludge process is your aerobic suspended growth system, right? This kind of questions can be framed for a multiple select question. Okay. Now let's see what's happening inside the activated sludge process. Okay, so we were here. Q0 amount of discharge is entering into the aeration tank. The value of BOD is S0 and MLSS concentration is X0, which is entering into the aeration tank. For the aeration tank, volume is V. V is the volume of aeration tank. X is the MLSS concentration inside the aeration tank. And once these microorganisms carry out the decomposition, the organic matter will reduce. The value of BOD of wastewater inside the aeration tank is S. Amount of BOD entering is S0, which have been reduced to S. The biomass concentration inside the aeration tank is X and V is the volume of the aeration tank. Okay. Now, this biomass is taken to the secondary sedimentation tank. Where the biomass, that is X, this biomass is settled inside the secondary sedimentation tank. Before the secondary sedimentation tank, the MLSS concentration entering is X. Now inside the secondary sedimentation tank, this biomass is settled and it produces the activated sludge. This biomass is settled and it produced the activated sludge. So the value of biomass that is entering along with the wastewater was X. Now out of this X, the biomass that is settled inside the secondary sedimentation tank, if you take out in the form of sludge, the concentration will be XU. And the amount of biomass leaving the system is XE. The amount of biomass leaving the system is XE. Okay. The reduction of BOD only takes inside this aeration tank. So BOD of the wastewater coming out from the aeration tank is S. Same wastewater is entering into the secondary sedimentation tank. It will only going to remove the biomass concentration. So the amount of BOD of the wastewater coming out from the secondary sedimentation is also S. For this sludge taken out from the secondary sedimentation tank, the value of BOD is S. Secondary sedimentation tank does not remove any amount of BOD. It will only going to settle out the biomass concentration. So again, S0 is the BOD entering inside the aeration tank. The BOD is reduced to S. And this S will be coming out with the wastewater, and inside the secondary sedimentation tank, whatever sludge is settled, this sludge will be of biomass. The BOD of the wastewater coming out from the secondary sedimentation tank and also along with the sludge has the same value of BOD, which is S. Okay. Now this sludge which is taken out from the secondary sedimentation tank, this is my activated sludge. So I'll write here, this is my activated sludge. This is my activated sludge. The discharge of this activated sludge taken out from the secondary sedimentation tank is QU. QU is known as useful sludge discharge. Now, out of this QU, some amount of discharge is recirculated back into the aeration tank. Some amount of discharge is recirculated back into the aeration tank. So QU is the discharge we are extracting from the secondary sedimentation tank. So QU is the amount of discharge we are extracting from the secondary sedimentation tank. Out of this QU discharge of sludge, some QR amount of discharge is recirculated back into the aeration tank, and the remaining sludge discharge is taken to the sludge drying bed or for sludge digestion, and that is known as the wasted sludge discharge, QW. The concentration of biomass in this wasted sludge discharge is XU. The BOD of this wasted sludge discharge is S. Okay. So QU is the sludge discharge taken from the secondary sedimentation tank. Out of it, QR amount of discharge is recirculated back, and QW amount of discharge is wasted out, right? Or it is taken to the sludge drying beds. Now when you observe this, so the total amount of discharge which is entering into this aeration tank is Q0 plus QR. So the total amount of discharge coming out from this aeration tank will be Q0 plus QR. Okay. And this Q0 plus QR is taken to the secondary sedimentation tank, from where QU amount of discharge is taken out. Okay. From this QU amount of discharge, QR amount of discharge is recirculated back, and QW amount of discharge is taken to the sludge drying beds. So the amount of discharge which is coming out from this secondary sedimentation tank is Q0 minus QW. This is the total amount of discharge which is coming out from the secondary sedimentation tank. So this is your entire mechanism of your activated sludge process. So let me just write down few things. Q0 is discharge entering into area or discharge from primary sedimentation tank. QU is useful sludge discharge. QU is useful sludge discharge. Then you have QW, which is wasted sludge discharge. QR is recirculated sludge discharge. X is MLSS concentration inside aeration tank. Then you have XU, MLSS concentration for in activated sludge. S0 is BOD of effluent from PST and S is BOD of aeration tank or BOD of wastewater inside aeration tank. So these are the few things that we will require for the analysis, right? So you should keep a check on all these things. Okay. Now when you look into this process, there is flow happening inside this aeration tank. Okay. V is also the volume of the aeration tank. So you can also mention V is the volume of aeration tank. So these are the details that we will require while analyzing for this activated sludge process. So when you look into this entire flow diagram for activated sludge process, you will observe that when the wastewater is entering into this aeration tank, there are different types of flow pattern that are maintained inside this aeration tank. Flow pattern is nothing but how the wastewater is flowing inside the aeration tank. Those are the flow patterns. So there are different flow patterns of wastewater inside this aeration tank. So next topic of discussion is flow patterns inside aeration tank. So the first flow pattern is known as plug flow. The first type of flow pattern that can be there inside the aeration tank is known as plug flow. Now what is plug flow? If this is my aeration tank, and from one end of the aeration tank I have applied the wastewater like this, okay. If the water is flowing in this direction uniformly without any mixing, if the water is flowing in this direction uniformly without any mixing, then this type of flow pattern is known as the plug flow. Means wastewater is entering into the aeration tank and from here onwards the wastewater just flows like this without any mixing, then this type of flow pattern is known as the plug flow. Okay, again, what is a plug flow pattern? When the wastewater enters into the aeration tank and without mixing, if the wastewater keeps on flowing like this type of flow pattern is known as the plug flow. In this plug flow, you will observe that in the initial part of the aeration tank, amount of food will be more. In the initial part of the aeration tank, the amount of food will be more because this food just brought in contact with the microorganism. Over the period of time, when this wastewater will reach the other end of the aeration tank, and in this part of the aeration tank, in the later part of the aeration tank, the quantity of food will decrease. The quantity of food will decrease and also the colonies of microorganism will increase, right? So we will observe this just by observing the quantity of food. In the initial part of this flow pattern, the quantity of food is more. In the later part of this flow pattern, the quantity of food will decrease because decomposition of organic matter has already taken place. Due to which what is observed is if you are traveling along the length, the F by M ratio, that is food to microorganism ratio, it keeps on decreasing as you move along the length of the aeration tank in a plug flow pattern. So again, this can be a question in your examination regarding, or this can be a statement in a multiple select question. What happens to F by M ratio along the plug flow? So if the wastewater is flowing in a plug flow pattern, then F by M ratio will keep on decreasing along the length of the aeration tank. So this is the first type of flow pattern. The second type of flow pattern that can stay inside the aeration tank is complete mix. The second type of flow pattern that can be made inside the aeration tank is complete mix. Now what happens inside complete mix is we mix the entire volume of wastewater. The entire volume of wastewater is mixed. This entire thing is mixed properly, right? So wastewater is entering into this complete mix like this. Okay. The entire volume is mixed. Due to this mixing, the contact opportunity between the microorganism and the organic matter increases. And if the contact opportunity between organic matter and microorganism increases, more active decomposition is observed and more removal of BOD is seen in this kind of flow pattern, which is of complete mix. For this complete mix, since you are mixing the entire volume of the wastewater, the F by M ratio is uniform or constant throughout the volume, in the entire volume. The F by M ratio is uniform in the entire volume of this complete mix. Okay. So these are the two types of flow pattern that exist for the aeration tank. Either the flow pattern can be plug flow, where F by M ratio is more in the initial stage and later on the F by M ratio decreases as we move along the length. Second type of flow pattern is the complete mix, where the contact opportunity between the microorganism and the organic matter is more, due to which more active decomposition can be seen in this complete mix. Since mixing is induced, therefore the entire volume is uniform, due to which the F by M ratio is uniform or constant throughout the entire volume of this aeration tank. Okay. So these are the two types of flow pattern that you see for an activated sludge process. Okay, now moving on with this, now let's see the section from where the questions are asked, and the questions are asked from the definitions of activated sludge process. So for definition of activated sludge process, let's start one by one. The first definition is your hydraulic retention time. The first definition of activated sludge process. So definition of first definition is your hydraulic retention time. So hydraulic retention time is defined as that time for which wastewater stays inside the aeration tank. I'll again repeat myself. What is hydraulic retention time? Hydraulic retention time is that time for which water stays inside the aeration tank. Hydraulic retention time is defined as the ratio of volume of the aeration tank divided by the discharge entering into the aeration tank, which is Q naught. V is the volume of aeration tank divided by Q naught, that is the discharge entering into the aeration tank. Second definition is hydraulic loading rate. Second definition is hydraulic loading rate. Just one second. So hydraulic loading rate is basically the amount of discharge applied per unit surface area, per unit cross-sectional area of the aeration tank. Hydraulic loading rate is defined as the amount of discharge applied per unit cross-sectional area of the aeration tank. Third one is your organic loading rate. Organic loading rate is amount of organic matter present in unit volume of the aeration tank. So the total amount of organic matter entering into the aeration tank is Q naught into S naught. It is Q naught into S naught. This is the total amount of organic matter entering into the aeration tank divided by the volume of aeration tank. So this is how you define the organic loading rate. So organic loading rate is Q naught S naught divided by V. The unit is kg per meter cube per day. This is how we represent the organic loading rate. So these are the three important parameters for this. You can note down this. Just note down this so we can see the another parameter. Next one is your specific food utilization rate. Third one is your specific food utilization rate, denoted by U. So it is defined as the amount of organic matter removed by the system. Amount of organic matter removed by the system divided by the amount of microorganism or the amount of biomass present in the aeration tank. Amount of biomass present in aeration tank. Okay, so let's start one by one. So amount of organic matter removed by the system. For that, first of all, we need to know how much amount of organic matter entering into the system. So when you look into this flow diagram, from this flow diagram, the amount of organic matter entering into the system is Q naught into S naught. Okay. Then amount of organic matter which is removed is, one, it is removed from Q naught minus QW into S. This is the amount of organic matter removed from here. And one more, QW into S. This is the amount of organic matter removed from here, right? So the total amount of organic matter which is removed by the system is the difference of amount of organic matter entering into the system and amount of organic matter leaving into the system. That is the total amount of organic matter removed by the system. So I'll write this. So specific food utilization rate U is equal to amount of organic matter entering into the system. So this is Q naught into S naught minus amount of organic matter leaving the system. So one is Q naught minus QW into S. This is one. Second is minus QW into S. So from two places the organic matter was leaving, divided by the amount of biomass present in the aeration tank. So this is equal to V into X. So specific food utilization rate U is equal to, when you solve this, you have Q naught into S naught minus S divided by V into X. This is your specific food utilization rate, Q naught into S naught minus S divided by V into X. This is your specific food utilization rate, right? After this, the next parameter is known as the sludge age. Denoted by theta C. So sludge age is defined as the amount of biomass removed from the system per day divided by the total amount of biomass present inside the aeration tank. So sludge age theta C is defined as, it is defined as mass of biomass or amount of biomass, whatever you feel like, mass of biomass removed from the system per day divided by mass of biomass present in the aeration tank. So this theta C is equal to mass of biomass which is leaving the system per day is QW into XU divided by mass of biomass present in the aeration tank is V into X, right? Now you will think like this, sir, for this removal of biomass, there are two areas. One is QW into XU, second one is Q naught minus QW into XE. For this, I would like to tell you, this XE is very negligible. Same, this X naught is also very negligible. So we can avoid X naught and XE for analyzing this system. So this is QW into XU divided by V into X. This is my sludge age. Okay. Next one is your F by M ratio. F by M ratio. This is also termed as food to microorganisms ratio. So food is nothing but Q naught into S naught. This is the amount of food entering into the system. The amount of biomass present in the system is V into X. So Q naught S naught divided by V into X is defined as the your F by M ratio. Okay. After this, we have one more parameter which is termed as sludge volume index. Next one is your sludge volume index. So sludge volume index SVI is simply volume in ml for the settled sludge in grams. Okay, so what you do is, from the aeration tank, you have this mixed liquor. You take 1 liter of this mixed liquor, right, inside the aeration tank. When you look into this diagram, from this aeration tank, you take out 1 liter of this mixed liquor. It will contain some concentration of suspended solids. Those suspended solids can be biomass. Okay, so you have to simply take out 1 liter of this mixed liquor and you have to measure the concentration of suspended solids. Here it is. So 1 liter of mixed liquor, 1 liter of mixed liquor is allowed to settle for 30 minutes. So you have this 1 liter of mixed liquor like this, right? You have allowed this mixed liquor to settle for 30 minutes. Then whatever solids are settled, these are the solids settled, right? These are the settled solids in 30 minutes. So what you need to do is, first of all, you need to measure the weight of these settled solids. First, you need to measure the weight of the settled solids, and that weight is nothing but your X. The second thing that you need to measure is the volume of these settled solids. The volume of these settled solids, right? So weight is measured in grams and volume of the settled solids is measured in ml. So this is how you calculate the sludge volume index. SVI is equal to V by X. V is the volume of the settled solids and X is the weight in grams of these settled solids. So this is what we have from the definition of sludge volume index. Okay, last is your equation of activated sludge process. So what is the equation of activated sludge process? 1 upon theta C plus KER is equal to U into Y. Let's see one by one what every term means. So theta C is your sludge age, Then KER is endogenous decay rate constant. U is specific food utilization rate. And now talking about Y. Now this Y you need to understand. For example, this is my organic matter. This is my organic matter. Microorganisms will attack over this organic matter. This is my organic matter. Microorganisms will attack over this organic matter and this organic matter will convert into biomass. Okay. Now this Y is that fraction of organic matter which is converted into biomass. So Y is fraction of organic matter converted into biomass. Y is fraction of organic matter converted into biomass. Y is that fraction of organic matter which is converted into biomass, right? So all these definitions are important. We usually see many questions from the standard definition with respect to the activated sludge process. Okay, so I hope you have found this session useful. A lot of content have been delivered with respect to activated sludge process. So just follow this video, watch this video for multiple number of times so that you have more conceptual clarity regarding activated sludge process. It is again one of the very important topic with respect to GATE-24 for environmental engineering. So this is all what I have to offer from my side. Myself Prateek Mishra signing off with a beautiful smile, and I wish you all the best for GATE-24. All the best. Do well.